Hello, good morning. It's a pleasure for me to introduce to Judith Karpen. She is the head of Space Weather Laboratory at NASA Goddard Space Flight Center. And she's at NASA since 2008, and before she was at the Naval Research Laboratory. And she has been working in many aspects of solar physics. Among others is numerical simulation of X-ray flares, MSD modeling of solar phenomena like formation of prominences, jets, CMEs, slow solar wind. I've been also working with her at NASA, and okay, that's all. Thank you.
Hey, thank you, Manuel, for the nice introduction, and hola IAC. Gracias por invitarme. So that's as far as my Spanish goes. I'm sorry. So thank you for inviting me to talk about space weather. I should point out that although I am the chief of the Space Weather Lab at Goddard, I am not an expert in absolutely every aspect of space weather, which is a very broad subject. My own research is, as Manuel pointed out, in solar physics. I started out doing flare research, data analysis, and then got entranced by the possibilities of computational physics. And so since that time, I've been working on mostly solar activity, mostly in the solar corona, the outer regions of the field. But it's been a great opportunity for me to learn about the broader regions of space that are outside of the just the solar atmosphere, as working with the Space Weather Lab. So the messages I want to leave, especially since there are so many students here, are as follows. The first thing is that the sun and the heliosphere really are interesting. My degree is in astronomy, and when I first went into astronomy graduate school, like everybody else, I wanted to do extragalactic work. I was going to do extragalactic radio astronomy, which was a big field, a hot field at the time. And then the guy who taught the class was incredibly boring, and I decided that I was going to do something else. So various ways I stumbled into solar physics and discovered that there's a lot of physics and a lot of fascination in that. And one of the neat things is that, yes, it's in the near field, which is kind of difficult in some ways, but it's also makes it, you're not as photon limited, depending upon what it is you want to do. You can always be photon limited if you try to reduce the, try to see the best resolution, the best cadence that you can. But we can resolve structures that are important. We can resolve a lot of the spatial scales that are important. For example, in the magnetosphere, we can resolve kinetic scales, particle length scales. So this is extremely important for understanding the physics. So another reason is that space weather affects you, it affects where you live, and affects where you work. Now, Spain, especially the Canary Islands, is at low latitudes. You might think, oh, we're not at all affected by space weather because all it does is come down at the poles. Well, that isn't true, and I'll give you some examples later on. And certainly if you ever use cell phones or other things that I'll talk about, you are definitely going to be affected by space weather. And last but not least, just as scientists, think of the sun and the heliosphere as a giant laboratory for plasma physics, for anything involving magnetized, ionized, and partially ionized, and neutral gases. And a lot of the processes that we study in space weather and in the disciplines within space weather are equally applicable to astrophysical objects all the way out throughout the universe. And I'll give some examples later on. So basically what I'm going to discuss is, define space weather. What is it? Why should we care about it? Then just sort of give an overview of how we fit within the galaxy. And then I'm going to go on and look at just sort of a chain of events. I'll talk a little bit about what the quiet sun does for space weather, but most of my talk will focus on the more eruptive and the more exciting parts of events that start at the sun and go toward the Earth, and how they affect each of the regions in between. At the very end, I'll just touch on the fact that space weather is now being explored outside of just the narrow region between the sun and the earth. People look at planets, other planets within the solar system, where we may go someday, either unmanned or manned space flights, and also even in exoplanetary systems. So why don't I start out immediately? So I looked into the history of the term space weather a little bit and found that people really were thinking along the lines of the analogy between terrestrial weather, you know, how clouds and climate and so on, and space or solar-driven weather for quite a long time, certainly since the middle of the 1800s. The first use of this term solar meteorology, which is pretty close to space weather, was from John Herschel, who's the son of the Herschel that discovered Uranus. So that's pretty, impressive that they started thinking that way early on, because they really didn't have a good idea of the underlying physics of most of the phenomena that linked the sun and the rest of the heliosphere, or even that there was a heliosphere. In the literature, the term was first used maybe in the mid-1950s. The term actually space weather itself, but it didn't really become popular until the 1990s when all of a sudden kind of the space agencies, the funding agencies, and the National Academy woke up and started realizing that there's a system science involved here that actually needs to be coupled. We're not just looking at solar physics and ionospheric physics, magnetospheric physics, space physics, solar wind studies as separate domains, but that these are all actually linked. And so their original definition really was, I think, too narrow as conditions in space that affect Earth and its technological systems. And I think by now people are looking beyond just the sun-Earth line, and the meaning should really be more that affect humans and technology from space to the ground, wherever that ground might be. Could be on the moon. So why should we care? So everybody kind of talks about space weather. You sometimes hear about it on the news. You hear if there's a big storm. I don't know if they do that here, since again people assume you're immune to it when you're at lower latitudes. But this very confusing diagram just shows a whole bunch of different phenomena, some of which I will talk on along the way as to how how some of our systems are affected and how our environment in the near and far space are affected by space weather. I'll just address the key phenomena because of the time limitations. So as I said before, we should be interested because it can harm a number of things. Here it just illustrates how it can harm spacecraft. And I mention this in particular because at IAC you have a number of groups that are specializing in building instruments for IR observations and for solar observations, especially the spectropolarimetry group. And a lot of these are flown on satellites. And you have to worry about what's going to happen to this extremely expensive, long-awaited instrument when it goes up into space. So the fact that you can have particles come in and damage the electronics, you can just get charging of the whole outside of the spacecraft due to the currents that it resides in, and the fact that even just the solar panels themselves can be hit by meteoritic dust and by charged particles can really ruin a lot of people's days and ruin somebody's work life for quite a while. Society also depends a lot on these on space weather, on satellites that are vulnerable to space weather. Now we have worldwide radio and television broadcasts, weather photography, lots of satellites up in the atmosphere that can monitor weather all over the globe. Communication satellites are essential. It's the only reason we're able to talk to people halfway around the world on our cell phones. We all use GPS, and now flights are increasingly automated according to GPS, which is a little bit worrisome. A lot of them go over the pole, And when you have precipitation of particles at that altitude, not only are you exposed to a lot more radiation, but you can't really afford to have a communications or a GPS blackout at a crucial time. As I mentioned before, scientific instruments are also vulnerable, and we depend on for our livelihood. And last but not least, humans. There's a lot of worry about how astronauts can receive large radiation doses if they happen to be outside of the shielding of the International Space Station, for example, at the wrong time. And as I'll talk about later, anybody thinking about going further into space is going to be increasingly vulnerable. You can't bring large lead blocks with you, at least if you're launching them from Earth. So as I mentioned last but not least, I think space weather also is a great laboratory for looking at compelling science. Just, the basic physics is complex. There's a lot of inter-regime coupling. You go from neutral to fully ionized plasmas, etc. So I just listed here some of the places in which astronomy and space weather, astronomy, and heliophysics can learn from one another and advance just our basic physical comprehension of the universe. So starting out with magnetic field generation and evolution, dynamos. We don't fully understand either how planets get their magnetic fields or why they lose their magnetic fields. And similarly, the way that stars differ quite a bit in the amount of magnetic activity and the amount of magnetic fields that they have. And then there's, of course, the extreme magnetic fields that you get in things like, neutron stars, etc. The galaxy itself has a magnetic field. How does that happen? We have magnetospheres all over the place. Other planets have magnetospheres. It's not entirely clear why some of them do, because they don't have active cores the way the Earth does. And of course, pulsars have magnetospheres, and some of my colleagues at Goddard in the solar group are working with people who do planetary magnetospheres to do some modeling and understanding of the processes. They are using the tools that we have. So another region is the fact that just like the heliosphere around the sun, which I'll show in a bit, we also have equal spheres of influence that come from all of the stars, and similarly also from the galaxy. So I'm going to be talking about magnetic fields a lot. Don't be worried. Don't be scared. I know that bothers astronomers sometimes. But this is really important. This is one of the major physical mechanisms by which space weather is governed, and also by which the entire heliosphere is linked. So magnetic reconnection, one of my favorites. I'm going to be talking about that in a little more depth later. That affects accretion disks, it affects magnetars, perhaps gamma ray bursts, the jets coming from them, and also jets coming from other astrophysical objects. Particle acceleration and shocks are extremely important, both within the heliosphere and outside of it. We need to know how cosmic rays are generated, where the gamma ray bursts come from, and how the gamma rays themselves are generated. And then shocks themselves, both collisional and collisionless shocks are extremely important, both for for the formation of supernovae and for the propagation of the remnants, and also bow shocks in a number of environments between interstellar clouds and stuff like that. And I didn't list examples here, but MHD turbulence is kind of a big fundamental region of research in both astrophysics and in heliophysics as well. MHD instabilities, Rayleigh-Taylor instability, Kelvin-Helmholtz, and more exotic ones pop up frequently because these are very fundamental to any time that you have certain conditions that are easily found in a number of phenomena. Okay, so let me just kind of put you in the context of where we're going to be talking about. So this is an artist representation of the heliosphere, and this whole big thing here is pretty much the heliosphere, and it's an elongated sphere because the direction in which the heliosphere is going sort of in this direction. I was asked to use the cursor because the pointer will not show up on the web streaming. And it's plowing through the interstellar medium. So there's a bow shock outside of it, of course. And then there's a structure that is elongated toward the tail away from the direction of motion. The region I'm going to be talking about is pretty much this purple sphere here that goes beyond the orbit of Pluto, although I'm not going to be talking about that because we haven't actually gotten there yet, probably out to the Oort cloud or something. And let's see, so this was done in 2012, this was the slide, and at that time Voyager had just reached the edge of the inside of the helio sheath, and there was a lot of argument about whether it was out in the interstellar medium and so on. So at this point, both Voyager 1 and Voyager 2 are further out, and they're starting to actually think that they're beginning to encounter interstellar material. So something I won't be talking about, but is also very exciting. So let's focus down in on the sun, which is the center of the whole heliosphere and the origin of all space weather. If you talk to stellar people, the sun is kind of a boring, average G-type star. It has lower than average amount of activity for a G-type star, and it's certainly much more of a weakling compared with dwarf M stars and others that are much more active and have a much greater magnetic field relative to their size. But I mean, look at this. This is not a boring object. This is one of the high-resolution images that you can now get from the Solar Dynamics Observatory. It's looking at plasma in the corona, the outer regions of the sun, that is about 1 million degrees Kelvin. I'm not going to go into every gory little detail of all the little features on here, but you can see that it's a lot more. It has a lot more features than you would guess from looking at the white light images, where it just looks like a featureless disk. This is the only star that we can study up close enough to see this kind of structure and to try and understand it. So the key to understanding all of this really is, again, the interaction between the magnetic field and the plasma. From all the way from the interior of the sun out through the corona and out into the heliosphere, all the way past the planets, etc. So all of the features that are shown here are really governed by the magnetic field. So I'll just point out some of the main features that are important. You can kind of see a big difference between the very diffuse-looking emission over here and over here. These are the two poles. And the reason is that these are areas where the magnetic field is basically open. One end is at the sun, the other end is out in the solar wind somewhere, and is dragged out. I mean, effectively it has to, you don't have a monopole, so the other end has to be, somewhere at the other pole, but they're considered open for all intents and purposes. And this is the region where the fast solar wind comes from. I'll talk about that in a little bit more detail later. The region that's a lot more inhomogeneous is the mid-latitudes here, where you see sort of two bands of bright but intermittent structures. These are the areas where the sunspots occur. What you're seeing here is the corona above these sunspots, and these are called active regions. Okay. I don't know why it stopped, but anyway. So these are called active regions, and they are all composed of closed magnetic field. So the long dark structures, let me see if I can drag this a little bit further. Nope. Okay. Doesn't like me for some reason. Okay, this one shows the long dark structures that are shown here and here and here. These are showing you regions where the polarity of this closed field is reversing. So in other words, you have a sunspot where you have a positive and a negative pole, and in between them is a line that we call a polarity inversion line. And what's interesting about those spots is that is where all of the excess magnetic energy that can be used to drive eruptions and drive activity accumulates. There's free energy over the rest of the sun as well on much lower levels that powers things like heating the corona and just sort of gives you the everyday normal emission from the sun. But we don't quite understand, in fact, one of the basic mysteries of solar physics and heliophysics in general is why does all the energy pile up just in these little narrow regions, and then, of course, why does it erupt? So to start with, one of the first things people noticed about the sun and that affects space weather is that it has a cycle. And I'm sure you've all heard about that. This is just illustrating with with stereo data, the years 2007 to 2014, at roughly 6-month intervals, except for the last one, which is a longer gap, because we were looking for a nice image. The change from solar minimum at the left all the way through to solar maximum. And you can see here that the movie that I showed before was really closer to solar maximum because it has these gaps, these regions at the poles were pretty absent from the coronal emission. They're just less dense and open field. And then you have all the active regions that are at lower latitudes. So the solar rotation alone, if you didn't have any changes in the active regions displayed on there, as it goes around, you're going to have variations in the output from the sun at different wavelengths. And this is showing in this picture, and I don't know how well you can see the detail, I'm sorry, that's so small. I was trying to squeeze it on here. That's showing the total solar irradiance. So that's integrated over the entire spectrum and measured and normalized over a bunch of instruments. And what this is showing you is that, yes, there is a variation over each of the solar cycles. You see more radiation at the peak of the solar cycle when there are more sunspots. That's what's listed at the bottom, than you do at the minimum. But in addition, there's a lot of variation in that image itself, in the plot itself, and all that is not error bars or errors in measurement. That's actually the variation due to the different amounts of active regions that are on the surface of the sun at any given time. They appear, they arise through the surface, and unfortunately, I won't have time to go through that. They evolve, and then they kind of decay and move toward the poles, etc. So you're going to get variations just from the active regions themselves popping up and disappearing, as well as from the 2 weeks that you see them on the disk that's facing you, and then they might go away. They might, next time it comes around, maybe you'd see it again. Next time it comes, usually they last for a few rotations at least, but sometimes they don't. So the quiet sun affects space weather in a few ways. The active regions themselves put out a lot of EUV and UV ultraviolet radiation. This actually, I'll go into it a little bit later, but this affects our upper layers of our atmosphere and determines, what the ionosphere is going to be doing, and even also affects things like the ozone layer and so on. Also, what kind of solar cycle you have makes a big difference. If you have a weak cycle, very low minimum like the last one, we get into regimes where the space weather is very different from what you're going to get when you actually have a strong solar cycle and you have a lot of eruptions and a lot of active regions and so on that can give you more emission. So the whole just sort of baseline for the atmosphere and for the geospace parameters changes as to whether you have a weak or a strong solar cycle. The solar wind also affects space weather. This is just sort of a standard. Parker showed that you're going to have to get a solar wind from a star, but it turns out that neither the slow nor the fast solar wind is exactly what the Parker solution would give you. The fast wind needs additional acceleration that doesn't just come from the open field solution that you would imagine, and that's still a mystery. The slow wind, we're still trying to figure out where exactly that comes from and what process gives that to you. So as the Earth goes around in its orbit and as the sun evolves, at different times the side facing the Earth, that's directly magnetically connected to the Earth, is going to be either in fast wind or slow wind. So we can vary as to kind of whether we're getting a strong push from the sun just in the background solar wind or a weaker push. And in addition, at the boundaries between the slow and fast wind, we get these sort of so-called co-rotating stream interaction regions. And those alone can give you geomagnetic storms simply because they're a high pressure region that can push on the magnetosphere, as I'll get into in a bit. Some of the unsolved problems in solar physics then, in the quiet sun part, is the origin of the solar cycle. We still don't understand exactly why they differ. Our dynamo models are incomplete and give contradicting results. Coronal heating is not understood at all, and coronal heating is necessary to understand why those active regions are bright in the corona. They could be little tiny reconnection events. They could be waves, turbulence, could be both. On a more practical level, people are still sorting out which solar features contribute to different spectral parts of the irradiance. For example, during flares, as I'll go into a little bit later, you get higher energy radiations than you do during quiet sun times. And as I mentioned before, both the fast wind and the slow wind are not really understood. So this is showing you kind of an eruption and artist's conception then of how that's going to affect you when you get out into the heliosphere and get to the Earth. This is showing the blob advancing on the Earth system, and this is showing you the magnetosphere and the CME impacting on that. Particles precipitating down to the aurora, to form the aurora, at one pole, and then precipitating down to the other pole as well at the same time. So that polarity inversion line thing that I talked about earlier was that underneath that dark filament that was seen to be erupting in the first slide there. And I'll go on to talk about some of the details in a bit. But mainly I just wanted to point out that these solar eruptions are pretty much the most destructive thing in the whole heliosphere as far as space weather is concerned. And the effects all the way along the way out in interplanetary space, all the way down to the ground, are what we're really trying to understand with the science of space weather. This is an image with a coronagraph on the outside showing you a lot of solar eruptions. And on the inside, although they're very hard to see, are the flares associated with these coronal mass ejections on the outside. And basically what you're looking at here is white light imaging of density enhancements. And what the CMEs really are not just density enhancements, but there's magnetic field associated with it. So these are large walls of increased density and magnetic field that are heading out from the sun in various directions. The flares, the brightenings down at the bottom, are related in a way that I'll get into in a bit. Oops, just skipped what I was going to talk about. Okay. So there's three different ways that these solar storms can affect the space weather and give you different effects outside. First, you have X-rays and EUV emission that come from the flares, the part that's down near the surface, and these get to the Earth in the radiate of the speed of light. So it gets to the Earth in about 8 minutes. The next thing, and I kind of did this in the wrong order, coronal mass ejection itself, as I said, was the plasma and the magnetic field that erupts above the flare, and those tend to take a few days to get to the Earth. They can go at speeds ranging from a couple of 100 kilometers a second to 3,000 or so kilometers a second for the fastest one. And the fast ones, the ones that are going faster than the ambient alphane speed, put out shocks, and these shocks can accelerate particles. And so we also have the third category, which are solar energetic particles, or SEPs, that are a very extremely important and very damaging component of space weather. And they can take usually about 20 minutes to get to the Earth. It depends upon where the shock is when they're created, usually by Fermi acceleration. So what I'm trying to show here really is just kind of that flares and CMEs are integrally connected. And what connects them is the process of radiation, of reconnection. magnetic reconnection. So here you can't even really see the flare itself, but it's down there on the surface, probably behind the limb. That is giving you, or that is part of the same process that's allowing the mass to be expelled in the CME that you see above, and the to give the brightenings and the radiative effects that you see below. The interesting thing in this image is that there is this gap, this black gap here in the observations themselves, and unfortunately that gap is is very hard to bridge, and that is exactly the region that we want to observe in order to understand where these things originate and how they originate physically. So that's one of the active areas of research, is how to bring the inner surface of the or the inner edge of the coronagraph observations closer to the sun, and also, as with SWAP from probe A, to get the observations of the corona out further so we can actually get an overlap and get rid of that gap. So what is magnetic reconnection? This is an extremely simple cartoon showing you how this process works. So basically, when you have oppositely directed fields or components of fields, when you get into a region where a diffusion or some other process allows the connectivity to be broken of field lines, then they can reconfigure themselves such that so that different foot points are now connected to one another than were originally connected. So here you now started out with the blue foot points being here and the red foot points being here and a field line between them. You end up with two field lines that are much shorter and have retracted, and both of them have red and blue foot points, as it were. And in the process, it releases kinetic energy. The kinetic energy then goes down to heat the plasma. You can also get particle acceleration associated with it, etc. So this is a very efficient way of reconfiguring a very large scale magnetic field, and also liberating energy, or allowing other ways of liberating energy in the process. So the most important thing here is that you're linking global and local scales. You have the local scale, you have to get down to pretty much kinetic scales, especially for collisionless reconnection, to explain how this breaking of the field lines and retying of the field lines happens. But these field lines actually are linked, or have foot points and are generated much further away, and so these are going to be having effects on much larger scales. So this is just a cartoon that I made. Ignore all the stuff on the right. I just wanted to show in a little easier way how the flare and the CME are connected. So if you get reconnection to occur somewhere along a current sheet here, and you need to have a current sheet or a null point in order for reconnection to happen, you're going to be able to reconnect field lines such that they can rise and accelerate outward, and you're reconnecting field lines that will retract and heat the plasma down below and give you all the signatures that are recorded as solar flares. So let me show you one model for how this happens, for the whole eruption process happens. We know that it's all magnetically driven, and we know, as I said before, that all the magnetic energy builds up around these polarity inversion lines. So this is a very simple kind of proof of principle that I've worked on. This is a magnetic field. It's very simple. It's a quadrupolar magnetic field, which means it basically is like having a big active region sitting on the equator of the sun, just with two poles, and then you have the background dipole on top of it. There's no solar wind in this calculation, etc. And so in this configuration, you're going to have two places where reconnection can occur that allow the CME to be expelled outward and the flare to go inward. This is a 2.5D calculation that we did with a code that has adaptive mesh refinement. I know some of you are working with that here. And that's absolutely essential for these type of problems because the current sheets are very thin. And if the current sheets are too thick, all you're going to get is diffusion. You're not going to really get reconnection. So in order to get excess energy into this system, what we had to do was to shear the foot points. In other words, move the foot points further apart, very much like would happen on the sun at these polarity inversion lines. Okay. The color in the plane is showing current density out of the plane. And what's happening here is that the overlying field is being removed by reconnection across the current sheet here. And that's allowing the core to bulge outward. And as this core bulges outward, it starts to stretch out the field in back of it. As the field in back of it stretches, then it thins down more and more until you can form a current sheet in back. And then when you form this current sheet in back, and I'll show that in a little more detail in a minute, that gives you the second reconnection region, which is a current sheet where the flare reconnection, or this reconnection that kind of separates the flare from the CME, occurs. Okay, so this is going to zero in on that same calculation, but just show you the region back here where the flare current sheet occurs and the eruption occurs. And as I said, this is just one model, but it's very similar. There are a number of models that utilize parts of this process to explain how these CMEs occur, how these solar eruptions occur. So just start this thing off. So this is during the phase where that overlying field is being removed by the reconnection above, and slowly the current sheet underneath is becoming longer and thinner and longer and thinner. Finally, it reaches the point where it's now at the point where we say, oh, okay, now I can diffuse away, I can change the connectivity of those field lines, and a miracle occurs and reconnection happens. So you get a lot of null points forming here. We don't just get one as we showed in that cartoon. And you also get shocks. You can see these sort of curved structures that were emanating from all of the plasmoids that were heading both up and down. And the CME itself then really takes off once this flare reconnection starts. So in the simulations, a number of the features that result were very comparable to the observations, and we're very happy with them. But there are still a lot of mysteries to explain. So here are the basic unsolved problems in these eruptions at the sun end, and the ones that relate specifically to space weather. So in order to predict them, we're going to have to understand first what the pre-eruption magnetic structure is, and that's something that the group here, the spectropolarimetry group here, is really specializing in, because we need to have excellent observations of the magnetic field at the surface and ways to extrapolate above the surface what this structure is. It's very difficult to do. It involves a lot of inversions and a lot of computational magic to get out of the data that you actually obtain the magnetic structure itself. But this is extremely important for the beginning of the process. CME initiation, as I said, the role of reconnection, there's a lot of arguments about what that is. Do you start out with, a fully formed flux rope in the atmosphere? Is it, does it have to emerge, etc.? Lots of arguments. It also is unclear how you get the very efficient flare reconnection, the flare particle acceleration. To explain the X-rays that you see, the hard X-rays that you get from flares, you need like up to 50% efficiency of acceleration, and that's really hard to explain with most physical processes that we know. So a lot of work needs to be done on that. When and where the shocks are generated. Most people know that the shocks are seen out in interplanetary space, and in our simulation, I didn't point it out, but we actually also form a shock out ahead of the CME. But there may be shocks that are generated very early in the process, low down, that can explain some of the poorly understood aspects of the solar energetic particles. Solar energetic particle acceleration itself, the transport. Why do we see SEPs so far away from where our models predict for a particular extent of a CME? Those are big issues. And last but not least, sort of the holy grail of applied space weather is what is the direction of the magnetic field when it gets to Earth? We know that the direction of the Earth's magnetic field, until it reverses every 100,000 years or something, we know exactly what direction that is. And if the magnetosphere, is going to be impacted significantly, if we're going to get reconnection, we know what direction that the field coming in at it has to be. But right now, none of our models are any good at predicting what that's actually going to be. So let me move on in the remaining time to the rest of the Sun-Earth system and talk about some of the responses to the eruption itself. So the important point here is just, and this is clearly not the scale, is that the Sun and the Earth are linked by, or have two separate magnetic field systems. The Earth is generating its own, the Sun is generating its own. Anywhere you have separatrices, you have separate flux systems, interesting things can happen. And so the interaction between the field that's carried by the solar wind, even at quiet times, you can get reconnection at the day side and on the flanks of the magnetosphere. And at times when you actually have an eruption coming off, then much more dramatic reconnection occurs throughout the magnetosphere, and I'll show that in a bit. So here, note that, and I'll show this better in this picture. This is actually a picture of the Jupiter magnetosphere or something like that, but it's much better than any of the other ones I could find. So the main point I want to make is that, again, just like we saw with the heliosphere, this is elongated in the direction away from the direction of the direction from which the solar wind is coming. So instead of the Earth system plowing towards the Sun, it's really more that the solar wind is coming out towards us. But in the frame of reference doesn't really matter. So the two places where the three places really where reconnection can occur and be very important are here at the front, and you can see that there's a change in direction of the magnetic field there, so that's ripe for reconnection and current sheets and so on. Up at the cusp, under certain conditions, you can get reconnection to occur. And finally, out in the tail, and I'll show a depiction of this, an active depiction of this, you can also get reconnection because you have a current sheet that always forms in this drawn out part of the magnetosphere. So this is somebody's depiction of, sorry, let me get that out of there, of how a solar eruption, which doesn't really show up, is going to impact on the magnetosphere. So here it is coming in, bang, the shock comes in first, and then the actual mass of this coronal mass ejection will come in, and you'll start to get thinning down you can start to get reconnection from the front. That helps to thin down the tail and back. The tail is thinning down here, much like that movie I showed you of the flare, and you start to get reconnection, and particles get precipitated down towards the poles to form the well-known aurorae. So now in the inner part of the magnetic field, the magnetosphere, we have the radiation belts. Now these actually did exist. They're basically areas where ions and protons are trapped. We generally have two radiation belts, and before these things actually existed, for a long time, but in the 1950s, people were doing atmospheric nuclear tests, which in retrospect was a really stupid idea, because what this did was add to the content of these radiation belts, extended them, and made them much more dangerous to spacecraft. That right after that we started the space era. And so some of the early spacecraft had a lot of problems with radiation damage and so on, and it's not a great place for people to go through either. In fact, recently we discovered with the Van Allen probes that there's actually a third belt. People had always thought, okay, there's just two belts, and they kind of evolve with time, as you can see in this movie. But they don't really even know why there is this third belt. So these are just some of the unsolved problems. The origin of these substorms, these reconnection events in the tail, which are what drive the aurorae and drive a lot of other action down at the ground. There's a lot of a lively debate in the magnetosphere community about that. They don't really understand what causes particles to get into and out of the radiation belts. There's a lot of observational work and theoretical work that's pointing toward wave-particle interactions. Again, another universal process that you need to know about in astrophysics as well as here. But the question is not entirely resolved as yet. There's energy transport in a number of ways, joule heating, there's currents penetrating, etc., from the magnetosphere at high latitudes, and somehow a lot of that energy does get transported down to low latitudes, such as we're living at here. And so those processes involve interactions between the ionized plasma and the neutral gas at different levels, at different heights, as well as at different latitudes. It's very complex, and we don't have enough observations of the global system to really understand that. In particular, we have very few observations of the zone that's kind of at the transition region between the what you'd call the ionized plasma in the ionosphere, which I'll get into next, and the neutral atmosphere below that. And we're trying, we should have some observations over the next few years in satellites that NASA is going to be flying. And so finally, as I'm going to show, another big question is, how do these variations in the magnetospheric currents actually cause problems on the ground? So people noticed a long time ago, for example, with the big Carrington event of 1859, the telegraph lines went crazy. There were currents going through those that actually harmed some of the telegraph operators. You students probably don't even know what a telegraph is. Sorry, it's an old form of communication before texting, and they also noticed a lot of other effects on magnetizable equipment. So people have learned since that time, as we made our equipment more sensitive and so on, that that there is a lot of damage done to the power grid, the electric power grid on Earth, and also pipelines, long distance pipelines in particular. And so one of the guys in my group has actually been working with the electric companies in the Northeast U.S. to install magnetometers on the ground at a number of their power sites. This is helping both science and the electric companies, because we're going to have a huge amount of data by this big network of magnetometers that's going to measure the magnetic field fluctuations associated with these large currents that get formed, these damaging currents that get formed in the grid. And the electric company will hopefully have some advance warning or find out some ways of mitigating the damage when these events occur. Okay, so finally I'm at the ionosphere. I'm not going to go into all the intricate detail of the lower atmosphere, the non-ionized region, just for lack of time, but I just wanted to point out that even though this is a very thin region, it's like 0.1% of the mass. This is the ionosphere, is basically where the ionized gas exists. Below that, all the gas is in a neutral form. This is extremely important for things like communications, for any of the interactions between gravity waves and other processes that occur down in the neutral atmosphere to transmit energy up into the upper atmosphere, into the ionosphere and above. So ways in which the ionosphere responds to a solar event. This is the tail end, let's say, of one of these CMEs coming in. Excuse me. Is, first of all, the flare, X-ray, and EUV emission ionizes more of the atmosphere, and so you just get a thicker, denser ionosphere. Well, what happens when you have a denser ionosphere is that the satellites going through it start to get more friction, and they start to drag more, and we have less idea of exactly where they are. You get a lot of currents, particle precipitation that deposit heat and also precipitate particles down from the magnetosphere into the ionosphere and the upper atmosphere at high latitudes, and that's how you get the aurora. And I just wanted to show you a nice pretty picture. This is the launch of the VISIONS rocket. One of the guys in my lab, it's a sounding rocket that they launch in order to understand the physics. And you can actually see the little streak here of the rocket itself being launched against the aurora that they were deliberately trying to fly into in order to understand it and get lots of neat data. So Other ways in which the ionosphere is affected is just that the transmission properties are changed, and so you can have radio blackouts, you can have GPS problems, etc. And finally, the UV, not only, the UV actually penetrates deeper, and so that affects things like the ozone layer and the stratosphere and other parts of the atmosphere. So all of these things happen associated with these space weather, these solar eruptions. Now, one thing that happens at low latitudes, okay, let me get moving a little bit. Low latitudes is these plasma bubbles, and these things mess up our communications, they mess up radar, etc. Oops. And they're basically Rayleigh-Taylor instabilities. They don't really understand them that well because, again, we need to have observations at multiple points that are also high cadence, have high cadence data rates. And we don't have that yet, but we're planning some missions now that hopefully will get better data on them. We don't know exactly why or where they're gonna occur, but we need to know that. So there's a number of unsolved problems. I already mentioned the plasma bubbles. The orbital drag is a big issue before and after these geomagnetic storms. The absorption of the EUV, again, because we don't have global coverage, we might say at this point we know what's happening when the EUV comes in, but we don't know what's happening over here, which has had totally different atmospheric conditions. So there's a lot of need, as you can see, for multi-point observations. It turns out that meteoritic dust is quite an interesting component of the upper atmosphere, and it can not only be used sort of as looking at individual metallic layers, you can use that as kind of an indicator of winds and other things that you might want to trace, but it also basically gives you the entire metallic composition of the, it provides the metallic composition of the atmosphere itself. And so we don't even know to within a few orders of magnitude how much meteoritic dust that is coming in at any given time. The driving from below is not well understood, again, because of lack of observations. And okay, I mentioned that basically in two different ways. So last but not least, people are working on magnetospheres, Mars, Jupiter. Mars doesn't have its own magnetosphere, but it has kind of remnant magnetic fields there, like the moon also does. There are different ways in which these magnetospheres are generated and maintained. We recently were asked by headquarters to provide space weather information at Pluto because New Horizons was going to be flying by in the beginning of July this past summer, and a few months before that, they said, do you think you could tell us what's going to, what it's going to encounter when you get there? And so people in my group took up the challenge and also asked for community help, and I'll show you what happened as a result of that. So this is using a model called NLIL, which is an MHD model where you can put in CMEs at 20 solar radii, and they follow their propagation, and solar wind, I should say, and follow the propagation all the way out to 40 AU, which is what you need to see Pluto. So these black blobs here are CMEs. The other little spiral features are these co-rotating streams, places where the fast wind is caught up with the slow wind and give you high density. And it's sort of zooming back to show you with time where New Horizons is and how it, what's going to happen when it gets to Pluto. But you can also see along the way there are other objects that you can predict the space weather at. They also predict space weather right now for the NASA missions that were shown in the first parts of this movie. And as it turned out, they had to put in about 125 CMEs to model the entire several months worth of evolution in the solar wind out at Pluto. And luckily, New Horizons got there during kind of a lull between events. So that was probably good for the spacecraft. So let me move on to the next slide. So I just wanted to make some basic points about, where do we go from here? I hope I've given you at least a taste of what goes on in space weather and what the interesting and important unsolved problems are. But you really need to have a combination of modeling, theory, and observations. Observations tell you what's out there, and that's the ground truth of everything you need to explain. It gives the theorists something to think about, and it gives the theories give the numerical modelers something to do. But without each of those, all of those components together, you're really not going to get anywhere. These days, it's too expensive for any one country to fly the kind of missions that you really need, especially to understand a linked, coupled system like this. So international cooperation is really essential. We're starting to get into using small satellites and constellations of satellites, and this is kind of an exciting direction that I think the whole world is going in. And this is really useful for places with local global coupling issues like geospace. Imagine if we had 1,000 little magnetometers up there, what we would learn about the variations in the magnetic field at any given time, how they're coupled to something along the same field line or on other field lines at the same time, things that we can't answer at this point. We also need more cross-disciplinary collaboration and cooperation. One of the examples I can give is that we have a group at Goddard now that was put together to work on space weather at exoplanets. And it involves astrobiologists, heliophysicists, earth scientists, atmospheric scientists, astrophysicists, planetary scientists, basically everybody from every field we could come up with, because you really need that. It has modelers, it has observers and theorists, etc. Just listed some of the examples in which cross-coupling can really allow us to make progress in a number of directions. And last, some of the students here may end up being astronauts. You might end up going to Mars or some other place there. I think you'd want to be warned ahead of time about how you're going to avoid being damaged by the by the harmful effects of space weather. And in order to do that, we have to really understand the causes and the consequences of space weather before even sending people out there, and how, come up with really good technological answers as to how you're going to mitigate these effects, either in space on the way to Mars, let's say, or on the ground, because Mars has no magnetosphere and no atmosphere, essentially, so you really have no shield the way we do here on Earth. So thank you for your attention. I'm sorry I ran a little over.
So thank you so much, Dr. Karpen, for this talk, and now we have time for a couple of questions, if you have any. Yeah.
I scared everybody.
Judy, thank you for this very, very nice lecture. I just would like to ask you about these plasma bubbles that you mentioned, the plasma bubbles,
yes,
in the low latitudes. So how widespread are they? I mean, do they cover the whole of the low latitude band around the Earth, or are they individual objects that pop up here and there?
They're more the latter. They seem to pop up kind of over, tens of kilometers in a particular region, over the course of like tens of minutes. So they're really, that's why they're hard to predict and they're hard to observe. You have to really have multiple spacecraft around to, you can't really anticipate where it's going to be at this point because it isn't fully understood. But these are the kind of things that have been blamed for some of the fatalities in military operations in recent years. There was an article in, I think, Science or Nature by Mike Kelly over the past year talking about a plasma bubble happening at a time when crucial communications were interrupted to Afghanistan. So it's important to understand them.
Thanks for the nice talk. So last night, actually, there was a program on the Discovery Channel talking about space weather.
And I missed it.
No. And they seem to be really worried about this. You mentioned it, about the pole reversal on the Earth. Okay, and they were saying, if this pole reversal happens, then we'll be vulnerable to CMEs and all this sort of stuff, which seem to be, and based on the simulations you were showing to Pluto, they seem to be chucked out once a day or two a day or something like that.
Yes, they're pretty frequent.
So is this something we should worry about? Or, should I stay up at night worrying that the magnetic field is going to change and we're going to get...
Well, first of all, I don't know when this field is actually going to reverse. I don't know
Right.
what they
They
said
said-
there,
they
but it
said
looks like
we're
it'll be
overdue.
tens of thousands of years
Yeah.
from now, roughly. I mean, there are indications that it's starting to get, I've read about it, and it's starting to get reduced. But basically, people are doing simulations of what happens when the magnetic field is tilted, on its way to reverse to the other direction. And so people are starting to look into that, what's going to happen in terms of penetration of solar wind and of particles, et cetera, down to the Earth's surface. I mean, it's not going to be good, I assume, but I wouldn't stay awake at night.
Okay, thanks.
Sure.
Hi, thank you. It's just a question about the last point. Can you really plan the space weather for a mission to Mars? It would take like 2 years or more.
No, I mean, you can't plan ahead to know exactly what's going to happen there, but in order to prepare for the mission, you need to think about how to make your spacecraft as least vulnerable as possible to the spacecraft damaging effects of solar particles, let's say. You have to figure out what to do about the humans. And that's a really big issue. Can you carry huge amounts of water that can absorb the radiation as it comes in, et cetera? What are they going to do in the event of some equipment getting knocked out? They're not going to be able to call for help. The communications back to Earth is really bad, and we'll probably only have one spacecraft going there. So those type of preparations, I think, are more planning for all possibilities and perhaps having monitors distributed more around the sun that would give you a better way of predicting in real time what is going to be going on in the direction of Mars and in the path. Right now we can predict for any satellite pretty much what the near-term space weather is likely to be. And for example, we do that for Spitzer, and we're going to do that for James Webb Telescope when it goes up to, just tell them if there's something that they can send commands up to turn the other way, or, whatever, there's something that's going to get damaged if they don't turn it off, we can do that. But those are within communication distance. Somebody going to Mars is not going to work very well.
Okay, thank you.
Sure.
Okay, so if there is not any other question, let's thank again Dr. Karpen for this talk.
Thank you.